In this section, we're going to look at Hess's law and enthalpy cycles. There are some situations where we cannot directly measure the enthalpy of a reaction. And so what we have to do is be very crafty and try and figure out what that unmeasurable enthalpy was. This is an indirect measurement of the enthalpy. Take, for example, this exothermic reaction. You can see in this energy diagram, we've got the reactants on the left and the products on the right. And what you can see is there's a red arrow going up to another line at the top. Now, what that line at the top represents is all of the atoms of the reactants separated apart. And so the energy change A is how much energy has to go in to break the bonds of the reactants into its raw ingredients. Then those raw ingredients will snap back together by electrostatic attraction and release a whole load of energy in the process. That's the black arrow B. And of course, if the chemistry is right that more energy is released in the forming of new bonds than the breaking of the original bonds, then there's a net energy output. It is exothermic. It will heat the environment around it. But if you look at this, it shows there's the level of the reactants in energy, the level of the products down there. Then the difference between those two levels, C, is the difference in energy between the reactants and the products. And though we might not be able to directly measure C, if we knew A and B, for example, then we could work out C. Because what you can see here is, for every bit of up that A goes, B comes down that same amount. And then beyond that, anything left over forms the value of C. It means that if I added A to B, I would get C, bearing in mind, of course, that B is negative. So this is called Hess's law, and it enables us to work out part of this reaction that we otherwise couldn't measure directly. So here is an example. If we had a reactant break into its individual atoms, and it required 100 kilojoules per mole of energy to do that, then we could add plus 100 on the side there. And then if we knew that a given out was 140 kilojoules per mole, which we would write as negative 140, because of the flow of energy being out rather than the flow of energy being in, and that's the situation where we would call it positive, then what you can see is the difference between these is minus 40. In this reaction, minus 40. So 40 kilojoules per mole will be given out. So how do we find this information? Where does this 100 and 140 come from? Well, someone has sat there working it out. If you go and find a really old book, but a fantastic book, it's called the Book of Data. It contains all of these energies so that you can construct these diagrams. Hopefully that all makes sense. You can see what I've done is I've simplified the diagram, top right there, reactants, the elements, and then the products. The elements are acting as an intermediate step, a step you have to break down the reactants into elements before they can join back together to form products. Now, chemists prefer to draw this same diagram without it being a reference to the energy difference. They draw it in this enthalpy change diagram here. You see, it's like a triangular diagram. The reactants on the left will break up into the intermediaries, which is the elements below, and then will reform into the products. And now basically that is what is actually happening, but if we weren't observant of the intermediate step, we would think the reactants are turning straight into the products, and indeed we could work out the enthalpy or the energy change that step would make, or we could find it, infer it by measuring the steps from the reactants to the intermediate step and from the intermediate step to the products itself. Let's look at a worked example of this. So this is very like the thermite reaction, but instead of magnesium and iron oxide, it's calcium and iron oxide. It's set off in exactly the same way. A magnesium ribbon sets it off, and it's probably going to get very, very exothermic. We can see that the iron oxide, in addition to the calcium, well, the calcium is more highly reactive, it's a displacement reaction, and it forms calcium oxide, and iron is left over. That's the reaction we cannot measure it directly. To be fair, we could do something like a bomb calorimeter and just measure the heat given off. But imagine that we couldn't do that for some reason. Well, we can find how much energy we're expecting it to give off through another way. We need to consider breaking the iron oxide into its individual elements. That's the intermediate step. Now, if we looked in the data booklet, we could find out how much energy is released when iron oxide forms. So basically, they would have probably used some sort of calorimetry in that instance. But what we want to know is how much energy does it take to break it back up again? It's going to be exactly the same. It's just going to be the opposite sign. So if in forming, what we have given out is 824 kilojoules per mole, then to break it is going to take 824 kilojoules per mole to break it into its constituent elements. Now you can see that we use the symbol here to represent that energy as its delta, the change, the enthalpy change of formation under standard conditions is 824. So the enthalpy change of formation from its elements to iron oxide is minus 824. But going from iron oxide back to its elements, it's the negative. So rather than minus 824, it will be 824 kilojoules per mole. The calcium in this instance is just elemental calcium. It's no bonds to break. It is just there. It has an enthalpy change of formation of 0. And so we're going to add minus 824 to 0, and that means the total enthalpy change. And what is represented by that arrow there is minus 824 kilojoules per mole. So let's look at the other side of this diagram. What are the energy changes involved in the formation of calcium oxide? Well, we can look that up in the data booklet too. The enthalpy change of formation for calcium oxide is minus 635 kilojoules per mole. It's exothermic. And so what we have here, you can see there are 3 moles worth. Now, if it's minus 635 kilojoules per mole, the total amount of heat given off is going to be, well, we're not going to have this because that's per single mole. We have 3 moles. So it's going to be 3 times as much heat as this given off. So we're going to do the enthalpy change of formation of this is going to be 3 times minus 635. This gives minus 3,810 kilojoules. Notice how I'm not displaying this as kilojoules per mole at this step. It's no longer per mole. This is minus 3,810 kilojoules for the 3 moles. And that's a little tiny detail. You've got to just make sure as soon as you start multiplying your enthalpy by how many moles, lose the per mole because it's no longer about 1 single mole of that substance. Now let's look at the reaction itself. So the iron oxide with the calcium, huge exothermic reaction, displaces the iron and forms calcium oxide. So what we can see is we're going to use Hess's law here, that A plus B equals C, which means that we can find A by doing C minus B. So the C was minus 3,810, and we need to take away minus 824. Now, a really key thing here is preserving the sign. Do not lose the negatives, otherwise you'll be taking away a positive number. It's very different to take away a negative number. It will go the other way. In this particular instance, that means this ultimately has minus 2,986 kilojoules per mole of heat given out. It's hugely exothermic, and we could work that out without even measuring it. Another thing that you could think about is that if you were going to predict how reactive something was and you didn't know, there'd be a safety concern. It might be so massively exothermic it could explode. But you could predict how much energy it's going to give out per mole by looking at this and applying Hess's law. Using the enthalpy of formation from the raw ingredients is one way we can use Hess's law. A second way we could use it is to look at what these chemicals might turn into if they went through a similar process, like, for example, combustion. The enthalpy of combustion could be used instead of the enthalpy of formation. Different from that example, we're not going down to the raw ingredients and up to something else that forms. We're going up to the products of combustion, which both the both of the chemicals, the products and the reactants, they will both burn, and so we can work out what the energy difference to those common combustion products is. So it's going to be very similar to the previous process, but this time we're looking at the amount of enthalpy change required to turn these chemicals into the products of combustion, like, for example, carbon dioxide and water. So think about this for the example of a hydrocarbon that we're burning. Both its raw ingredients, the hydrogen and the carbon, will undergo combustion and form carbon dioxide and water, but so will the hydrocarbon molecule itself. Look at this energy diagram over here. The hydrocarbon molecule breaks down into its elements and forms the products of combustion, just like before. Now, what we can do is we can work out what that enthalpy change of combustion is, C, by just rearranging Hess's law. In this case, A, which is the amount of energy required, and as demonstrated by this picture at the top here, we're identifying the amount of energy required to go from the elements to the hydrocarbon. Well, we can find out by looking at B and C, which are known. So specifically, if we were going to burn paraffin, we were interested in what the enthalpy change was from the formation of paraffin from its elements. Then what we could use is the enthalpy change of combustion for both the carbon, the hydrogen, and the paraffin itself. The next stage would be to draw an enthalpy flow diagram. And so here we are. We're going to use this information taken from the data booklet at the top in the table. We're going to add it to our diagram. To start with, let's look at the paraffin at the top right. The paraffin has an enthalpy change of combustion of -2877. Clearly, it gives out energy when it's burnt. And that would produce the products of combustion, water, and carbon dioxide. When we look at the elements themselves, both carbon and hydrogen would burn. A thing that you have to remember is different here is whereas there are no enthalpy changes of formation of raw elements, there is enthalpy change of combustion of raw elements because they will all combine with oxygen to form the products of combustion. So with this method, we have to remember to multiply by the number of moles of the individual elements. So 4 moles of carbon added to 5 moles of hydrogen gas. And so in working out the sum of the combustion enthalpies, we could do 4 times -394 added on to the 5 times -286. It means that, of course, burning carbon and hydrogen is exothermic, -3006 kilojoules. And again, because we're not talking about 1 mole, we're burning several moles of this substance. It's a net energy rather than a rate of energy compared to how many moles. So we don't use the per mole, we just use the kilojoules. Now, of course, because A equals B minus C, then we could do -3006 minus -2877. And so we get -129 kilojoules per mole. So in the formation of paraffin from its ingredients, it's slightly exothermic, but not nearly as exothermic as burning either of the two. Now here is a subtle detail, and it's worthwhile practicing with a few examples to really firm these up. There's different rules. Hess's law appears differently depending on the construction of whether or not we're talking about enthalpy change of formation or enthalpy change of combustion. You see, with formation, it's going to be products minus reactants. With combustion, it's reactants minus products, simply because of the direction of the energy arrows. So you can see that in the top right diagram, it's products minus reactants because the arrows are pointing upwards, and it's reactants minus products because the arrows are pointing downwards.